Kia ora guys, here's the fourth video for today. This is one from 1974 scholarship calculus, and this is a nice question. Maybe a little bit more thinking than a couple of the other ones I've done today, but still pretty obvious what we've got to do once you've got the techniques under control. So this one's going to use logs and implicit differentiation, and what else? A little bit of chain rule. No, not really chain rule, just logs and implicit. Okay, so what we've got is a situation with x, a, b, and y, and so all of these things are positive real numbers, so not a complex numbers question, and we have to prove that the derivative with respect to x, dy by dx, is equal to y over x, as long as this is not the case. So this probably should give you a clue that we're going to end up with a fraction, and we might be avoiding a denominator of 0. So let's see where we might start. Well, this looks pretty awful as it is. We've got x to the a, y to the b equals x plus y to the power of a plus b. So I don't want to work with it like that at all. It's going to be horrible trying to do implicit here and here. So I'm going to take logs on both sides. So if we take the natural log on the left-hand side and the natural log on the right-hand side, this is what I start with. I get a plus b times the natural log of x plus y. Now this is still a bit yucky because it's got x's and y's mixed in, but it's already looking way better. Using my log rules, I can split the left-hand side up as follows. A log x plus b log y is equal to a plus b log x plus y. So now we're going to go through and differentiate each term with respect to x, and we're going to start here. So the first one's easy. It's going to be a times 1 over x, right, the derivative of this. Now the next one is an easy implicit one. I can't differentiate log y straight away with respect to x, so I differentiate it with respect to y, and I get b over y times dy by dx. Right? So the flow through is going like this. X is affecting y, which is affecting log y, like this. So it's just standard implicit. Now the next one I'm going to write like this. This is a constant, so it's going to be a plus b times the derivative of this with respect to x. Right, so leaving the left hand side as it is, what does that give me? Well, when I differentiate a log, this is the inside function. So it's going to be a plus b times 1 over x plus y. And now I have to do the chain rule. I have to differentiate the inside function with respect to x. So let's do the x. That gives me 1 plus the derivative. I need another colour pen. The derivative of this with respect to x is dy by dx. So that wasn't really so bad. Now what we've got to do now is like the one we did in class today, where we have to collect up all the terms that have got dy by dx. And it's worth going back and checking where am I trying to get to. Right, well I want to show this very simple thing that dy by dx is equal to y over x. So let's see what we've got. Well, on the left hand side I've got a over x. I'm going to do some expanding before I collect up. Plus by times dy by dx plus, equals a plus b over x plus y plus a plus b over x plus y times dy by dx. So now I'm going to gather up this term with this term and get these together as well. So let's bring all of the constants, or the no dy by dx's, over here. So we've got a over x minus a plus b over x plus y, chuck brackets around that to be careful, equals dy by dx into a plus b over x plus y minus b over y. Right, so I'm bringing this to here, this one to here. Common denominator is the next step, so x times x plus y gives me a times x plus y minus x times a plus b. And that equals dy by dx times, common denominator, y times x plus y, y times a plus b minus b times x plus y. At this point, you've got to be hoping that a whole lot of stuff is going to go away, because this still looks bad. But it's not cognitively challenging stuff, right? It's just expanding. So my good year 9s could do this. Hello, year 9s, if you're watching. There we are. Seriously, if there are any year 9s watching, please come and talk to me. Right, here up the top, what have we got there? Well, we've expanded all of that, and lots of that's going to disappear. Right, so here we've got ay minus bx over x times x plus y is equal to dy by dx. Well, these are going to go, leaving me with ay minus bx. So I'm starting to like this a lot, over y times x plus y. Cross multiplying, I get y times x plus y times ay minus bx over x times x plus y divided by this. So look at that, we're just about done. And now we get to simplify, boom, boom, like that, and we're left with dy by dx is equal to y over x. But we've got to be a little bit careful. It's fine for me to sit here and go like this, but we can't do that if we've got a problem if this is 0 or if this is 0. So we just need to write down that that derivative is not defined in two situations. The first is if ay minus bx equals 0. In other words, if ay equals bx, which is what we started with. The other one that we should just look at and then reject. Or if x plus y is equal to 0. But if you go right back to the start of the question, I told you that all of those things, all of those four things, were real positive numbers. So that means that we know, and that means strictly positive numbers, that we know that that condition is never going to be a problem. So it's just the provided that ay doesn't equal bx. So there you go, some straightforward algebra once we get the hang of it, but I think a really good example of how you can do implicit differentiation there. Now I've skipped you straight through into some quite hard implicit problems. If you go to, you know what I'm about to say, Education Perfect or Khan Academy or the Delta textbook or the A-level textbook, it will start off much, much more gently. Thanks for watching. I might do a couple more before we go away. We'll just see how we go. Just let me know if there are any problems.